Welcome to this explainer. I'm absolutely thrilled you're here. You know, as a research scientist, I spend a massive chunk of my life just looking at molecules. And if there's one fundamental truth in organic chemistry, it's this. A molecule's structure is the absolute key to predicting its chemical destiny. Today, we're focusing our analytical lens on haloalkanes and haloarenes. We're going to break down their structure, their reactivity, and the basic physics of the carbon-halogen bond to give you the ultimate edge for your exams. Let's get started. Now, before we dive into the dry chemistry and all those reaction mechanisms, let's talk about why this actually matters in the real world. Because these aren't just abstract drawings on a chalkboard, right? Halogenated compounds literally shape our environment and our health. For instance, in clinical synthesis, chlorine-containing antibiotics, like chloramphenicol, are absolutely vital for fighting severe systemic diseases like typhoid fever. And even inside your own endocrine system, your body needs natural iodine to synthesize the hormone thyroxine. Without it, you develop a severe goiter. And in synthetic applications, these compounds are the backbone of modern medicine, from synthetic malaria treatments like chloroquine to essential surgical anesthetics like halothane. Seriously, from microscopic soil bacteria to our global atmospheric layers, these compounds are everywhere. So here's our roadmap for today's explainer. We'll start with the core bond engine, classify our structural types, look at synthesis pathways, dive into substitution mechanisms, talk about the resonance shield, and wrap up with the real world and environment.
Section 1. The core bond engine. To understand any machine, you really have to understand its engine. And in our case, the polar carbon-halogen bond is the fundamental engine driving all the chemical machinery we're about to study. Think of halogens, fluorine, chlorine, bromine, and iodine, as incredibly greedy magnets. They pull electron density right away from the carbon atom they're attached to. This creates a built-in polarity. You get a partial negative charge on the halogen and a partial positive charge on the carbon. And that electron-deficient carbon? Well, that is a glowing target for nucleophiles, which are just molecules desperately seeking positive charges. But notice the trends here too. As you move down the periodic table from fluorine to iodine, the atomic size increases. This makes the bond longer, stretching all the way from 139 picometers to 214 picometers. And as that bond gets longer, the bond enthalpy, or the bond strength, drops significantly. Basically, an iodine-carbon bond is way easier to snap than a fluorine-carbon bond.
Now, there's a massive fundamental divide between haloalkanes and haloarenes, and it's all based on hybridization. In haloalkanes, the carbon is sp3 hybridized. It's aliphatic with exactly 25% S character, which means it holds its electrons relatively loosely in a pure single bond. That makes it highly reactive to any incoming nucleophiles. But look over at the haloarenes. Here, the halogen is attached directly to an aromatic ring with sp2 hybridized carbon. That carbon jumps up to 33.3% S character, pulling those electrons in way tighter. Plus, it forms a partial double bond, which shortens the bond length down to 169 picometers. The end result? It is extremely resistant to nucleophiles.
Section 2. Classifying structural types.
Think of this structural taxonomy matrix as your ultimate visual anchor. Identifying the exact type of carbon neighbors is a totally essential step for predicting which reaction pathway a molecule will take on an exam. Up on the top row, we have our sp3 carbon-halogen bonds. You've got your standard alkyl halides, which can be primary, secondary, or tertiary, depending on their carbon neighbors. Then you have allylic halides, where the halogen is on an sp3 carbon strictly adjacent to a double bond, and benzylic halides, where that sp3 carbon is attached directly to an aromatic ring. Down on the bottom row, we've got our sp2 bonded halogens. Vinylic halides are bonded right to the double bond carbon, and aryl halides are bonded directly to the aromatic ring. Definitely memorize this matrix. Recognizing these structures is literally half the battle in organic chemistry. Section 3, synthesis and preparation methods. Okay, so what if you actually want to build an alkyl halide in a lab? Well, starting from an alcohol is a classic Route 1. You've got options. You can use HCl with zinc chloride or phosphorus triarpentachloride. But honestly, focus your attention on thionyl chloride or SOCl2. This is the preferred elegant route. Why? Because when you react your alcohol with SOCl2, the byproducts are sulfur dioxide and hydrogen chloride, and both of those are escapable gases. They literally just bubble out of the reaction mixture, leaving you with a wonderfully pure alkyl halide left behind. No messy separation required. It's fantastic.
Route 2 relies on hydrocarbons. Now, a quick warning. If you try free radical halogenation of an alkane using chlorine gas and UV light, you are going to get a nightmare. It yields incredibly complex, messy, isomeric mixtures that are intensely difficult to separate in the lab. A much cleaner, way more reliable method is the addition of a hydrogen halide, like HX, directly to an alkene. This neatly follows Markovnikov's rule, where the halogen attaches to the more substituted carbon, giving you a predictable, singular product. Section 4. Mechanisms of nucleophilic substitution. Okay, let's dive into this mechanism. It's a beautifully simple two-step dance. Step 1, attack. Step 2, displacement. An electron-rich nucleophile, seeking out that polarized, positive-leaning carbon center we talked about earlier, attacks the carbon. And in doing so, it forces the halogen, which acts as our leaving group, to be displaced, taking its electrons with it. And here's a quick pro tip for your exams. Always watch out for the embident nucleophile, like the cyanide ion. Because of resonance, cyanide can attack via the carbon to form alkyl cyanides, also known as nitriles, or it can attack via the nitrogen to form isocyanides. Tricky, right? Keep an eye out for that.
Now this table right here, absolute gold mine. It perfectly contrasts the two main substitution pathways, SN2 and SN1. SN2 is a bimolecular, concerted, one-step process. The nucleophile sneaks in from the back, causing a complete inversion of configuration. Think of an umbrella flipping inside out in a strong wind. And because of this backside attack, SN2 strictly prefers unhindered primary substrates. SN1, on the other hand, is a unimolecular, slower, two-step process that actually forms a carbocation intermediate. And because that intermediate is perfectly flat, the nucleophile can attack from either side, leading to racemization, a 50-50 mixture of stereoisomers. SN1 relies entirely on carbocation stability, so it heavily prefers highly substituted tertiary substrates.
But here's a crucial point. Substitution isn't the only possible outcome. If you take a haloalkane and heat it up with alcoholic potassium hydroxide, it won't substitute at all. It undergoes beta elimination. The halogen and a hydrogen from the adjacent beta carbon are ripped away simultaneously to form an alkene double bond. Another amazing alternative is reacting with metals. Reacting an alkyl halide with pure magnesium in strictly dry ether forms a Grignard reagent. These are hyperreactive, incredibly useful tools in organic synthesis. But notice I said dry ether. Literally, even the tiniest trace of moisture will instantly kill a Grignard reagent, converting it into a totally useless inert hydrocarbon. Section 5. The haloarene resonance shield.
So why don't haloarenes undergo nucleophilic substitution easily? Well, there are 4 structural reasons that perfectly paralyze the carbon-chlorine bond. We can think of it as a resonance shield. First, the resonance effect. Lone pairs on the halogen delocalize right into the benzene ring, giving the carbon-chlorine bond partial double bond character, making it physically harder to break. Second, as we saw earlier, sp2 hybridization holds those electrons much tighter. Third, phenyl-cation instability. This means SN1 pathways are just impossible because the self-ionizing phenyl simply cannot be stabilized by resonance. And finally, electronic repulsion. That electron-rich pi cloud of the benzene ring acts as a literal physical shield, repelling any incoming electron-rich nucleophiles.
So pop quiz time, just to test your understanding before the big exam. Since we know halogens are highly electronegative and they generally withdraw electrons, effectively deactivating the benzene ring, where on Earth do incoming electrophiles, molecules that are actively seeking electrons, attach if they try to react with a haloarene? Take a second to think about that.
Got it? The answer lies in what we call the halogen paradox. Yes, the halogen deactivates the overall ring compared to pure benzene due to its -I, or inductive withdrawing effect. However, the resonance effect, the +R effect, pushes electron density specifically into the ortho and para positions of the ring. Therefore, any new electrophile, whether it's through halogenation, nitration, or sulfonation, will be strictly directed to attach at those activated ortho and para sites, yielding a mixture of isomers. I know, it's completely counterintuitive at first glance, but it's actually perfectly logical when you look at the structure.
Section 6. Real world and environment. Let's zoom out to the global scale and look at this environmental persistence scale. Over on the left, we have dichloromethane, which is a really powerful industrial solvent. It's highly volatile and can harm the human nervous system. But structurally speaking, it breaks down relatively quickly once it's in the atmosphere. In the middle, we've got freons, or CFCs. Now, these are highly inert locally, which is what made them such great refrigerants, but they're globally catastrophic. They rise totally intact into the stratosphere and initiate these massive radical chain reactions that just devour the ozone layer. And on the far right, DDT. Because of its bulky, halogen-heavy structure and that exact resonance shielding we just talked about, it is totally resistant to breakdown by soil bacteria. The terrible result? Permanent bioaccumulation in the food web. To bring this all together, look at this capstone spectrum. It visually summarizes everything we've mapped out today. On the highly reactive left side, you've got your 1-degree aliphatic haloalkanes, primed for rapid SN2 inversion. In the middle, 3-degree haloalkanes reacting via SN1, alongside those stabilized allylic and benzylic halides. And way over on the far right, the stable, resonance-shielded sp2 bonded haloarenes and polyhalogens that are practically inert to nucleophiles. We've seen how the exact same elemental ingredients can behave completely differently based solely on their architectural arrangement. As the quote goes, the same electronegative pull that makes aliphatic haloalkanes dynamic engines for organic synthesis is paralyzed by the resonance of haloarenes, creating stable pollutants that refuse to break down. So I'll leave you with this final provocative thought. As future researchers and scientists, how do we balance the vital, life-saving medical utility of these incredibly dynamic compounds against their dangerous, unyielding environmental permanence? Thank you so much for joining me for this explainer, and best of luck with your studies.